Sure. Yeah.
Okay, welcome everyone to the morning session. So Jan Vonk will continue his lecture on modular curves, rational points on modular curves. There are a couple of quick announcements. There's a group photo today at 4. I'll announce it again at 2:30. And there's a special dinner after the last lecture. Okay, so over to you.
All right, thank you very much. And welcome back, everyone. So I'm going to continue the story that we started yesterday. And I put again on the board this table that we had on yesterday about the torsion on certain types of modular curves. And so we learned yesterday about cusps on modular curves. And we learned that there is the theorem of Manin and Drinfeld, which we proved that all the cusps on any modular curve associated to a congruent subgroup always generate torsion points. So all the divisors supported at the cusps are torsion in the Jacobian. So this we showed, and then we tried to make that theorem effective. I feel like I'm very loud. Is it just me, or I see? It's okay. If it doesn't bother you, it doesn't bother me. So we tried to make that theorem effective using Siegel units, and we went through some calculations where we saw that on some small examples, we can actually figure out the structure of the cuspidal torsion, which happens to be the same as the full torsion in the Jacobian in all of these examples. So I made a little table here for all the modular curves in this range for a prime ranging from 11 to 23. Anything less than 11, the modular curve will be genus 0, so it's not very interesting. And starting here, I've tabulated here the genus of x0 of p and the genus of x1 of p. So you see, here we have two genus 1 curves, and that's the example we started off with on the very first lecture, the E1 and the E2, the famous x1 of 11 and x0 of 11, which we already discovered had 5 torsion, and that's what this entry of the table is, okay? Then if we keep on going, you see that J0 of 13 is actually trivial because x0 of 13, as we know, is just a projective line. So there's nothing interesting to say here, but downstairs here, there's a lot of interest. And that's what we'll talk about also today. x1 of 13 is a genus 2 curve, and it happens to have a rational point of order 19. I put the rest of the table here also because the goal really of these lectures is to sort of continue approximating Mazur's paper in a better and better way, starting off with this column, and that's what we'll focus on, what we were already starting last time, and then moving on and sort of going up in difficulty one by one. And every time we do that, we see a new sort of technical difficulty arise that we have to circumvent. So today we'll go as far as this column, but I encourage you to keep going further. So 17 is one where really new phenomena arise. Maybe 23 is also an interesting one, and then at 37, you'll have to overcome another obstacle. And at that point, you'll be pretty close to Mazur's full argument. So it's really a nice way, I think, to approach this. And so last time, we started off with the modular curves of level 11. And so for that, we looked at the pair of dual 5 isogenies. Starting with x1, where we quotient out by its rational point of order 5, we had a z mod 5z on this side, to obtain x0 of 11. This is the natural forgetful map on modular curves, where we send the point just to the subgroup that it generates. There's a dual 5 isogeny to this one. This one has a 5 rational point, but the kernel of it is something else. It's a mu 5. It has to be really by the Weil pair. And so what we did last time is we considered this isogeny here, this phi. And today we'll look at the dual isogeny. And in fact, we already showed that the group that we obtain by taking x0 of 11 q, so the Mordell-Weil group of that curve, quotiented out by the image of the irrational points under this isogeny phi, is actually just, well, I'll just write it 5. It's of order 5, you know, which is what we expect because we already know that the rank is supposed to be 0. That's what we're trying to prove. Okay. Now we saw that for this argument, if we were to flip around everything, and that's what we kind of ended on last time, and we were to flip the Z mod 5Z to a mu 5, we were in trouble with the Étale topology. And we had to slightly refine it to the flat topology in the hopes of being able to use Kumar theory to get the necessary estimates on the flat Selmer groups. And so that's the argument that we'll continue today. So for the dual isogeny, the dual isogeny going from x naught of 11, and I know that this has good reduction outside of 11. So I still get an abelian variety over Z1 over 11. And we're looking now at the isogeny again. So this is between the abelian varieties, extending them coming from the neuron model. There's still abelian varieties. So we have a very nice surjection here. And the kernel of it in the generic fiber was mu 5. And we saw last time that there's this trick about which you can find more in the notes, that the kernel of this map, where we spread it out over this larger arithmetic ring, it's some finite flat group scheme, and we know that it agrees with mu 5 in the generic fiber. We saw last time that that's enough to conclude that, in fact, this remains a mu 5 over all of this ring, and it's because the ramification index is small. It's 1 in this case. It's strictly less than p minus 1, which is 4, and therefore this theorem of Orton-Tate applies. So we get this dual isogeny. I'll still call it phi hat. And we're going to play the same game in the hopes that just taking on as a black box the facts that I listed at the end of last lecture, the flat cohomology will now give us the required estimate. Now, if we look at what we're trying to estimate is the Q points of this one modulo the image of the Q points of this one. So what's our expectation of what the size of that group is supposed to be? Well, you see, the rational point here of order 5 is still here after this isogeny. So we expect that actually on Q points, this map is onto. So we're trying to show that the quotient, where I flip around these two, is not on F5, but it's actually 0. That's what we're trying to show. So we need a pretty sharp bound on the Selmer group. Yeah? We want the Selmer group to be trivial. So let's see if it is. Okay. So, like we said last time, we need to look a little bit deeper at the prime 5, which I've already included here in this ring. Now we get the following, and I won't put it on this board, I'll put it on this board because there's going to be an extra term added later on. So what do we get? We get, on the one hand, x111q modulo the image of phi. So taking z1 over 11 points is the same as taking q points on the generic fiber, as we saw last time. So this is the image of phi hat. And we know that this injects. By working in the flat topology, all we have to do is change the subscript. And we have coefficients in the kernel of this isogeny, which is mu phi. And that's good news. Because just like in the first lecture, the very first lecture when we proved the weak Bordeaux-Levay theorem, we relied on Kumar theory to make sure that we knew what this group was. Yeah? And we relied on the right exactness, for which we had to invert 5. There wasn't a 5 then, but the equivalent of 5. Now we haven't done that, but we've changed the subscript, and that allows us to use Kumar theory anyways, giving the same conclusion that we're working here with the units modulo 5th powers, just like in the first lecture. And the units in Z, of course, there's not very many, there's plus or minus 1, but the 11 units here, there's also 11. So there's powers of 11 here, and here there's 5th powers of 11. So the quotient, very nicely, the plus or minus 1 is a 5th power, comes out to be an F5. Okay. All right, so that's already a little bit better, right? If we had kept 5 here, so if we inverted 5 also, this would have been an F5 squared. That's the Selmer group we would have written down naively as in Silverman using Étale cohomology. Now we've already gotten it down to an F5, but that's still not quite good enough because we suspect that this group here is actually trivial. We can't quite conclude that from having injected it into something of order 5. So our trick that we came up with last time of working in the flat topology is not quite strong enough. So we have to do a little bit more. Well, there's only one place left to go. The final frontier, it's the prime 11. So now we're going to go deeper, not just at 5, but also at 11, the final bad prime that we need to consider. We really have to get the required estimate. Okay, so now what I'm going to do is I'm going to add a component to this diagram. I'm going to have a map here to the corresponding local points over Q11. Okay. And we're going to play the same game. Which gives me a diagram of this form. This should be a Q11 now, with coefficients in mu5. And the diagram like this commutes. And for similar reasons to what we saw before, just like in the first lecture, we have an isomorphism between this cohomology group. The next one is the Picard group, so it's trivial. And then we get Q11 star modulo 5th powers. Now, Q11 star modulo 5th powers, that's a little bit bigger, right? And that's because you see, when you decompose Q11, you also get this Teichmüller lift. You get the 10th roots of unity, which modulo 5th powers is something else. And then you get the units, and then you get the powers of 11. So from both of these factors here, you get an F5 squared. So it's a little bit bigger. But it seems like we're worse off somehow by going through this other side of the diagram. We actually land in a group that's even bigger. But the point is that it would be very nice if we could show actually that this group was already trivial. We don't really know that this map is injective necessarily, but we know that this map is injective, this map is injective, and actually, this map is also injective. So all three of these maps are injective. This map is injective because here, this F mod 5 is generated by 11. And 11 is not a 5th power in Q11. So this is also an injection. So if we could argue that this group here is 0, we'd be completely done. And that's the way Maser argues. We'll look at this group. Now for this one, we will look at the Néron model. Yes, and now we have no other option. It's got bad reduction at Z mod 11Z, but we can still extend it by using the Néron model. And we know actually already quite a bit about the special fiber of it. We had a picture of it up on the board during the first lecture. Okay, so looking at the fiber at 11, we get a commutative diagram where the fiber at 11, I'll decompose in the usual way by looking at the ZP points of the Néron model, which surject onto the FP points by reduction modulo P. Yeah, I wrote P, but I know what P is. It's 11. And the kernel of that, by using the formal group, we can identify with some group M0, which is a pro-11 group. It's Z11 squared. Sorry, Z11 in this case. Actually, why don't I write that? That's maybe a little bit less mysterious. Additive group Z11 inside. We get a similar diagram also for X1. We're just dealing with elliptic curves, so this is all from Silverman. And we'll consider now also the maps going across in the vertical direction. This is F11. induced by this dual isogeny by hat. Yes. And of course, these groups here, that's the same as the groups in the generic fiber. Yeah? So the co-kernel of this map is what we're trying to bound. We're trying to show that this is surjective. Okay, so first observation, you see, this phi hat, if we compose it once more with phi, we make the diagram continue, the composition here is just going to be multiplication by 5. Now, multiplication by 5 is invertible on Z11, additive group Z11. So therefore, this one already, to begin with, had to be an isomorphism for purely formal reasons. So we know already that we're trying to bound the co-kernel of this one. This one is already an isomorphism. So we get that one for free. So the co-kernel here is trivial. So all we need to know is what the co-kernel of this one is. We know the co-kernel of this, we have the snake lemma, and we have that the co-kernel of this one is wedged between 0 and whatever this guy is, hopefully also 0. And therefore, we can conclude that the co-kernel is actually trivial. And now the point is that this one, let's call it star, is surjective. Yeah? The special fibers of these neuron models are not so mysterious. I mean, we have a 5-gon for x naught of 11. And for x1 of 11, we had this 1-gon. Sorry, I didn't draw the donut, but that's above this point, and this one's above the special. And so here we just get a 1-gon. Yeah, these were the Tamagawa numbers that went into our verification of the Burton-Swinnerton-Dyer conjecture in the very first lecture. And so we have a map here. On the component groups, it's certainly surjective. Yeah, you get from a Z mod 5Z down to just one component. But if you count points already, you see that you have to be surjective. How many points are on this one? Well, there's 10 points on each of these GMs, right? And there's 5 of them. So there's 50 points on them. This is a group of order 50. This one is a group of order 10. And the kernel here on this side can be at most 5, yeah, because it's a 5 isogeny here. So already, you know, it's got to be surjective. The kernel must be all of Z mod 5. So there's a Z mod 5 here, and this one is actually onto. And so is this one. So by the snake lemma, we conclude that also this group here is actually trivial. Okay, it's that co-kernel. And now by the commutativity of this diagram, we can conclude that this group here is indeed equal to 0, as we require. Okay, and then we proceed in the usual way. So we deduce, for example, we've now gotten both sides of the isogeny, both phi and its dual. We estimated the co-kernels, and so we deduce now an estimate, just like we do when we do a descent by 2 isogeny on elliptic curves. For instance, if I take x naught of 11q, and I quotient out by 5 times x naught of 11q, then I get a map from this naturally, because there's a containment of the kernels here, to x naught of 11q, to phi, which one was phi and which one was phi tilde? Let's see, phi, what I need, of x1 11q, just because there's a containment between these kernels, so that's a surjection. And the kernel of that, there's actually a map. The map is phi hat. Sorry, it's phi, from x1 of q, modulo, I'll just write the image, phi hat. And not necessarily injective, but it will have to be, I guess, because we already showed what both of these groups are. Namely, this one's still on the board here. That one is 0. And this one here is an F5. So therefore, this one must be an F5. So it follows the Mordell-Weil theorem that, well, we've already found a point of order 5 on it. That's the point of order 5 on x1 or on x0 of 11. Modulo 5, it survives, and so it already spans the whole thing. So the rank is indeed 0, and this is the full Mordell-Weil group. So let me just write it as a kind of conclusion. We showed using these arguments that this guy really is a Z mod 5Z. And this guy really is also a Z mod 5Z. Last time, or the very first lecture, I bluffed and I told you that this was true by a 2 descent. And of course, nowadays we do a 2 descent on an elliptic curve. Certainly, these are elliptic curves by a simple press of a button. Here we did everything by hand. If you were to write out the 2 descent by hand, it would take more than the 4 lectures, I think. It's very complex somehow. And specifically this example, I did it, but it's very, you have to pass through this cubic extension, which is totally ramified at 2. You have to write down representatives for everything, modulo squares in that ramified extension. It's really very, very painful. So we forget that when we press the button. But in fact, even practically speaking, this is almost a better argument than doing a simple 2 descent on these elliptic curves. But mostly the benefit of this is theoretically speaking. And this is because this is the way Maser would have done this descent. He would have proved that it was rank 0 in this case. It represents sort of a first approximation of the general arguments that Maser gives to show that there's, yeah, sorry. Yeah, so implicit in this is that I've already determined all the torsion. Yeah? And that's usually easy because we have lots of methods by reduction modulo 2, etc. So I've not done this, but I was sort of assuming this from the first lecture that we already know that the Z mod 5Z is the full torsion. This we can usually determine. It's the rank that's the tricky part. So I'll take on faith that we know what the torsion is in this kind of argument. Okay, so if we want to prove, or if we want to determine what all the possible orders are of a point on an elliptic curve over Q, a rational point, then we've already showed here that there's no rational points on this one, because these 5 rational points were all taken care of by cusps. There were 5 rational cusps on this one. So we found all of the rational points. There's no others. And so in particular, we find that there is no elliptic curves over Q with a rational point of order 11. If we keep going, maybe we can also rule out that there's elliptic curves with a rational point of order 13. And that's the subject of today's lecture. We'll get inspired by this kind of argument, which may have seemed overkill because we were dealing with elliptic curves, but it's the one that really generalizes in full. And it exhibits a lot of interesting structure on the Mordell-Weil groups of Jacobians of modular curves. Okay, so this is the theorem that we're going to talk about in the remainder of this talk. Well, hopefully, there's some time also to say something else at the end. And it's a theorem that was proved by Maser and Tate. And as I said yesterday, it was inspired by Ogg's calculation of precisely this entry in the table. So Ogg had determined, using techniques very similar to Siegel units, he was using actually maybe a slight variant of it. He was looking at Eisenstein series. It's a slight variant of this argument. But he had determined that there was a rational point of order 19 on the Jacobian J113. And he went to Harvard to give a talk about it, and both Maser and Tate were there, and they found this an amazing fact, and they said something like, oh, if this Jacobian has a rational point of order 19, which is so large, it's not entitled to have any other rational. And then they prove it in their paper using a 19 descent. So this is the theorem. What am I writing? There are no elliptic curves E defined over Q with a rational point of order 90. Yeah? And the arguments are very similar, but already there's an extra step needed. And every time you go one up, you need an extra step of Mazur's argument. Sorry, 13, sorry, thank you. This is also true, but that was actually already known. Yeah. That was known because you see, well, okay, I'll get to that later. The point is that was known because x0 of 19 is an elliptic curve. So you can map it down to the elliptic curve, do a 2 descent or whatever you like there. Maybe a 3 descent is a little bit better, actually. From that, people had already concluded, I believe, that there was none of order 19. But 13 they couldn't do because the strict didn't work, you see. X naught of 13 is genus 0. That didn't work. But anyway, that's just an aside. Okay, so what we will do is precisely the same trick. So we will use the modular curve x113, and we will show this is a genus 2 curve, as you can see in the table on the left. And there's 2 steps in the argument now, where the second step is no longer automatic. The first step is similar to what we just did. We'll use a 19 descent on the Jacobian, J1 of 13, and I don't want to keep writing that, so I'll just call that A from now on. To show that A of Q is actually entirely torsion. It's only this 19 torsion point that Og found. Okay, so once we know that, we now have to conclude something about the rational points on x1 of 13. Now that's no longer automatic. Before we had the luxury that x1 of 11 and j1 of 11 were the same curve. Now something has to happen. And that's now step 2, is we will show how this implies that x113 of Q actually consists precisely of the rational cusps, of which last time already we determined there's precisely 6 of them, because that's p minus 1 over 2. There are 6 rational cusps and then 6 cusps that are rational over the real cyclotomic field of degree 13. So Q zeta 13 plus, which is a degree 6 extension. So it's precisely the 6 rational cusps. That's what we're trying to show. Okay. Now, to do this, if we look at all of the steps, clearly, I mean, we'll need to know a little bit about the 19 torsion on this abelian variety A. And we already know something. We know it has a rational point of order 19. But the 19 torsion, it's a 4-dimensional space over F19. And we know it has this one trivial line. But what else is in there? We're going to have to dig deeper inside of the 19 torsion on this Jacobian of x113. And to do that, the large endomorphism ring, as usual, will help us out. Okay. So the curve x1 rather 13 has lots of automorphisms. They come from the moduli interpretation that we have for them. The first kinds of automorphisms are the following. So if I have my elliptic curve E together with a rational point P of order 13, I can take a number A that's not divisible by 13, and I can just multiply the point by that. I can do this. And I can do this for every A in Z mod 13 Z star, and of course plus or minus won't act. So I'm really acting with something in this group. Now these are called the diamond operators. They're extremely important Hecke operators. As we'll see today. Sorry. So we'll use them to our benefit. In this case, it's very concrete. So they give us an automorphism group. By the way, an automorphism group defined over Q. that is cyclic of order 6. Now, this is a cyclic group of order 6. It's generated by 2, for example. So those are the first very important operators that will help us. A second class of operators are sort of lifts of an Atkin-Lehner involution on X naught. And they arise as follows. So they depend on a zeta, which will be a 13th root of unity that is not 1. And what we can do is we can take EP and we can send that to E modulo the subgroup generated by P. And now I have to pick a point of order 13 on it. It's not so clear how to do that. Yeah, I have the points of order 13 on E, and I can map them through, but I don't know which one to pick in the line that's left over. So I'm going to pick Q, where Q is determined by the demand that on the original curve, if I lifted it, Q tilde and P, and here it doesn't matter which lift we take, had Weil pairing equal to zeta, where zeta is an element of mu 13, again, not 0, not 1, and again, up to inversion. If you invert it, you'll get the same point by the same reason that we had. Again, this will give us some automorphisms. They're all involutions, actually, but they're not defined over Q. Yeah? So they're automorphisms. They have to be defined. This zeta has to be in the field of rationality in the moduli problem. So they're really automorphisms over Q zeta 13 plus of this curve x113. And so together, these generate a dihedral group of order 12 inside of the geometric automorphism group of x113. In fact, that's the whole geometric automorphism group, but we won't need that. All right. So by this excursion into automorphisms, we suddenly see that the Jacobian A that we're interested in has lots of endomorphisms. In fact, it has lots of rational endomorphisms even. And one of these will be the endomorphism with respect to which we do a descent. In this one, yeah, it's one orbit. Yeah, so it's a simple Jacobian. It's not geometrically simple. So if you go to Q square root 13, I think it splits as it's bi-elliptic, but over Q it's simple. I see. You want to know the full endomorphism algebra. Yeah, absolutely. Completely. Yes. Exactly. So in fact, we could also make this precise and we could find the full automorphism group or the full endomorphism group of the Jacobian, but we won't really need that it's the full one. I'll just use the ones that we have available. But indeed, you're completely right that nowadays it's known that that's actually the full endomorphism group. Yes. Thank you. All right. So from this discussion, you see, for instance, if A is equal to 2, it generates this group of order 6. Yeah? So we got a cyclic group of order 6 inside of our automorphism group. So that means that we obtain really an injection of Z zeta 6, which is also known as this ring, inside of the endomorphism group over Q of A. Yes. And we're looking at the prime 19. So multiplication by 19, that kernel we'd like to understand. But 19 in this endomorphism ring it's actually a principal ideal domain by accident here, but it doesn't really matter. It's helpful. It's a little bit helpful, but it's not super important. It splits as the product of two prime elements, pi and pi prime. So 19 is split in this order because, well, 19 is 1 mod 3, I guess is the easiest way to say that. Now, because of this, we find a very nice endomorphism, namely pi. And so we get an endomorphism from the abelian variety a priori over the generic fiber, but then I spread it out to an isogeny over the abelian scheme that I get over Z 1 over 13. So I'm staying away again from the prime of bad reduction, and these are actually abelian schemes. And the kernel here is something, yeah? So it's A pi. And we'd like to understand a little bit better what A pi is, what the structure of A pi is. So we know now that this A19, the full 19 torsion of this abelian scheme, it now splits up actually as A pi, the kernel of pi, and then the analogous kernel for the other element, pi bar. Both of these are two-dimensional. So that's already a little less daunting than this full four-dimensional thing. Two-dimensional, or rank 2 really, if I've spread them out. And we know already that there's a point of order 19 in this module, a rational point of order 19. That's what we get from this table. Now, this rational point of order 19, it's the full torsion. Yeah? Hasse-Weybounds will tell you there's no other torsion. And so if you act on it by pi, which is defined over Q, either it kills it or it preserves it. Yeah? Well, I guess if it kills it, it preserves it as well. But the product of pi and pi prime is multiplication by 19. So that has to kill it. Yeah? So one of the two has to have this rational point of order 19 in its kernel. I don't know which one, but at this point, I don't care which one is pi and which one is pi bar. So I switch them if I have to. And I have this rational point of order 19, and I'm going to assume, without loss of generality, that it lies inside of A pi bar. I'll consider this one, but I want the rational point to lie in the other one. Okay. All right, so we're going to do a 19 descent with the usual formalism on this. So we're going to land in a flat cohomology group with coefficients in this A pi. So now I'd like to understand what this A pi looks like. It feels like I haven't understood anything because I've put the only thing that I understood in the other one. Now I want to know what's in my kernel here. Now this kernel can be nicely filtered. Okay. Into a short exact sequence. Which takes my mystery module, A pi. And what I'm going to do is, you see, I have this nice line, this Z mod 19Z inside of this one. Now I'm going to take my other automorphism, W zeta, and I'm going to map it to wherever it goes. Now it's very easy to show, because this is a dihedral group, you act by inversion here, that that image is going to lie in my module. So W zeta of this will lie in A pi, and that's because this zeta will act by conjugation on the pi. So it'll switch from this factor to this factor. And of course, there's a choice of a zeta involved, but it doesn't matter which choice you make. Any other choice will just be a translate along this line. So it'll be the same module. So a priori, because this thing is not defined over Q, it would seem that this W zeta of Z modulo 19Z wouldn't be defined over Q at all, but in fact, it descends to something over Q by what I just said. So that sits inside of there, certainly. What's the quotient? Well, the quotient actually we can also write down. And you can find more details on this in the notes, but it's not difficult to argue that in fact, this can also be seen as the kernel of a certain natural map that exists on this, which is the Weil pairing. Where T is some chosen generator of this rational subgroup of order 19. Yeah? So it's a rational point. I take this T, and I take the Weil pairing inside of this full A19, and the kernel of that is three-dimensional. Now this guy is already self-orthogonal, as you can show, it's in the notes. And so there's an additional one-dimensional kernel inside of here, and it's this one. So the map here, because it's the Weil pairing, goes to mu19. Looks like this. Everything I said was really over the generic fiber, but then we spread out again over Z 1 over 13 with the same arguments we used before. to obtain actually this short exact sequence of group schemes over Z1 over 30. Okay. All right, so very beautiful picture. I realize I went a little bit quickly here, but there's a lot of technical things to check here. You know, the self-orthogonality of this one, the fact that it spreads out. I'm treating that with a very light touch here. You can find more details on that in the notes. I just want to focus on the main ideas of the descent. So this is what this module looks like. Now, this is great because you see this mystery module here, at least we filtered it with pieces that we can understand completely after some finite base change. Mu19, we understand completely. And if we estimate the FPPF-Selmer group of this one, already we'll know the ones of the filtered pieces. This one we'll know by Kumar theory. This one we'll know after we pass to the finite base change that trivializes this. So this W zeta lies in mu13. So if I pass to this cyclotomic field, it's actually going to be the trivial module. It's going to have trivial Galois action. And that's in general what Mazur calls an admissible module. It's a module we can understand. It's something you can filter by pieces that after some base change become either Z mod PZs or mu Ps. And both of these, the cohomology groups, we can understand. So that's kind of a first peek at one of the general notions that's very important in Mazur's paper. Okay. Okay. So we're now dealing with a descent argument, just like before. And it gives us, again, a commutative diagram that'll look very familiar. So passing to the long exact sequence for this one, in flat cohomology, will give us that we have a diagram where we take the Z1 over 13 points of this, which is the same as the Q points. We map it by this endomorphism pi, also to the Q points. And we'd really love to understand the cokernel of this, and the cokernel injects into this flat cohomology group H1 of, well, I'm working over the base Z1 over 13, and I'm valued inside of A pi. It's a much more complicated module than we had before. Okay. Now, also the bad prime will play a role. We do the same thing we did before, giving us a commutative diagram of this form, where these are the natural maps going to the localization. This is still pi. And here we have the corresponding flat cohomology group. Q13 with values in A pi. And here, of course, I've spread out over the Néron model. Right? So I'm dealing with a bad fiber. There's a map going across here. Okay. Now, just as before, there's two maps here that are relevant. Well, this is pi, but let me call it 1. Maybe I'll do it in a little bit of color, actually. Let me call this map 1. And let me call this map 2. Okay, now, what do I expect the cokernel to be? A of Q modulo the image of pi. Well, my 19 torsion point, which I suspect is the only thing in the Mordell-Weil group, is not in the kernel of pi. So I expect that this guy is on 2. So again, we're in this situation where we have to have a bound that's so good that it's 0. We have to get the 0 bound. So we'd like to show that this cokernel is 0. Alas, maybe this one will turn out to be a little bit too big as before, but not to worry. We already know that as long as we can show that this guy is on 2 and this guy is injective, we have the same argument as before, and we can conclude that in fact, A of Q modulo the image of pi is trivial. All right, so this is a little diagram chase. So I'll do both of them in turn. So the first is that this map 1 is surjective. That's step number two. Step number one. And step number two is that that map is injective. Now, for step number one, there isn't really much new needed. It's the same trick that we used also before. So we use a diagram where we take the neuron model, and it's Z13 points, yeah, which is the same as the Q13 points of the generic fiber, this guy. And I'm going to map that to the FP points, so the F13 points, in other words, which is a surjection. The kernel of it, just like before, it's some group, M, which is a pro-13 group. Yeah? So it'll be like Z13 squared, the formal group isomorphism. Now, I also have the same arrow. I'm just going to copy what I just wrote. It's the exact same diagram. But I'm copying it because, of course, I have maps vertically connecting these two diagrams. Like so, where this map is really now the map just induced by pi. Get a unique map induced on the neuron models, I'll still call it pi. All right, so that's the guy that we want to show is onto. Again, the snake lemma will help us out as long as we can show that this is onto and this is onto. All right, now, same reason as before, these are pro-13 groups. So if I take the dual isogeny, which we've called pi bar, I'm just multiplication by 19, which is an isomorphism on my pro-13 group. And so therefore, this guy, again, for the same reasons, has to be an isomorphism. Yeah? So we know that the co-kernel here is equal to 0. That much. What we need to know is the co-kernel here. And before we just drew a picture, and it was kind of clear just from counting points, even very naively, that's not a luxury we have anymore. So here's the trick that Maser uses. He says, well, instead of bounding the co-kernel, why not bound the kernel? After all, these are two finite groups of the same order. Yeah? So the co-kernel is going to be 0 if and only if the kernel is 0. So if we can show that the kernel is 0, we're also good to go. Well, but now we flipped the diagram upside down. Yeah, we've got a 0 here, or we think we have a 0 here. We definitely have a 0 here because this is an isomorphism. So what do we need to know? That this is injective, actually. Yeah? So that this is injective here. And why is this injective? Well, you see, we actually know the kernel. That's the point. We know the kernel of this. It's this group scheme that we had. It's a pi, but spread out over this thing. So all we need to figure out is if you look at that as a Galois module, let's say. We take this a pi. All we need to know is we need to figure out what the kernel is of the corresponding Q13 maps. That's what we want to know. Well, that's the fixed part of the decomposition group above 13. That's what we need to know. So that's going to be the kernel of this map, which we suspect is trivial. Now, why is that true? Why is that 0? Well, we don't have to deal with this module very much because, in fact, we filtered it with two pieces that we understand quite well. So all we need to know is what the D13 invariants are of the two flanking terms. And if we can show that those are both 0, then we're done. So that's what happens in the argument. So this is true. Oops. Because we have actually two equalities here. If we look at this W zeta, Z mod 19Z, D13, and we look at mu 19, fixed by a decomposition group above 13, then both of these must in fact be 0. Why is that? You see, if this had a non-trivial fixed part, that would mean that 13, the prime 13, would be split in the cyclotomic field Q adjoins zeta 19, which it's not, because 13 is not 1 mod 19. So this guy must be trivial. There's no decomposition invariance. For the same reason, it's true here, but here we have to pass to a different extension. We want to trivialize this action here. Here we had to go to the cyclotomic field. To trivialize this action here, we had to go to a different cyclotomic field, namely Q adjoins zeta 13. So this only has invariance in the delta if so both of these are actually 0, these filtered pieces, and therefore we can conclude that this guy is also equal to 0. Therefore, the kernel here is 0. Therefore, the kernel here is 0. Therefore, the co-kernel here is 0. And therefore, the co-kernel here is 0, as we wanted. Okay, so it's a bit of a complicated diagram chase, but that's the basic idea. So again, the core issue was to understand what A pi does. And because we filtered it by 2 pieces, we can understand after a base change, we can understand we're good to go. Actually, I don't know why I didn't continue there. Oh, I remember. It's because people on that side can't see this board. Okay, well. Okay. So what we're left with is step 2. Yeah? We have to show that this map 2 that we had in this diagram is injective. That's what we need to show. Again, the same ideas for the 5 descent, but kind of on steroids, a little bit enhanced, but it's really the same core ideas, just using the filtration. That's the new step here. Okay, so 2 is injective. Now it suffices to show that both of the corresponding map on the filtered pieces are injective. So meaning going from Z1/13 cohomology to Q13 cohomology. If you can show that both of these are injective, then we conclude the same for the middle term. The same reasoning we've used time and time again. So what are these maps? Well, we have flat cohomology, first of all, of Z1/13 with coefficients in this strange translated module, point, like so. And then going to coefficients that are the same, but for Q13. And well, I guess I'll write it. So this is Z1/13 with coefficients in U19 going to the flat cohomology of Q13. Now this one is very familiar. That's exactly the same one we did with different numbers in the first 5 descent. Yeah? So that's just Kumar theory. So this one we've already done. It's injective. So the only one we have to deal with is the top one. Why is the top one an injection? Yeah, and you see, here we just have to use one extra step. We don't understand this module very well, but we understand it very well after we pass to the cyclotomic field Q joint zeta 13. That's where we understand it, that's where it becomes constant. So all we need to do is pass through that cohomology group and understand what we lost in that process. And in fact, we didn't lose anything. And this argument, you see, it all looks fancy because it's fancy cohomology and everything. But it's exactly the same argument that Silverman uses time and time again. For instance, when he shows that Selmer groups are finite, you always pass to this finite extension where you trivialize the module and then you kind of analyze what you lost along the way. He just does it with Galois cohomology, but it's the same here, same kind of argument. Okay. Yeah, so for the former, there's actually an exact sequence that tells us precisely what we lost. So note that over this ring R, which is Z, where I invert 13, that's the base ring that I had before, but now I'm also going to join zeta 13. Yeah. That's actually an étale extension of Z1/13. So our group that we're trying to estimate for Z1/13 with coefficients in this bizarre module. We can just restrict this module to this covering. And that gives us a map to the R cohomology, where now the coefficient module has become trivial. In fact, I know even more. I know that I land in the G fixed part, where G is the Galois group of this étale extension. So G is the Galois group, let's say, of Q zeta 13 over Q. I guess I'm being a little bit sloppy here. It's really only Q zeta 13 plus that we need, but it doesn't matter. Both work. Okay, and so the kernel of this, we understand also. The kernel of this is going to be precisely H1 of G with values in the H0 of this Z mod 19Z over the extension, which is just Z mod 19Z. We didn't really lose anything by passing to this extension because you see, this is a cyclic group of order 12 acting trivially on Z mod 19Z. So it's homomorphisms from Z mod 12Z to Z 19Z. That's trivial. This one is 0. So you get actually an isomorphism between these. And now you can just check it for trivial modules, the injectivity. Yeah. Now, actually, the injectivity, sorry. Let's check it because something more is true. This module actually is completely trivial. Yeah, so is the middle one, because this one is trivial. So that's going to help us a lot, because checking the injectivity now just becomes checking on the co-kernel, which we already have. So actually, this module is going to be trivial. So showing that it's injective into something else is not very difficult. Now, why is that? This is a more arithmetic kind of argument. So we note that, in fact, this cohomology group with coefficients in Z mod 19Z. Yeah, I mean, what is this? It's a module we can understand very well. In fact, it's a smooth group. So the étale cohomology or the FPPF cohomology, it's the same. So if you don't like it, you can just put étale here. We're looking here at Galois cohomology, really. Galois cohomology over this cyclotomic field with values in Z mod 19Z. Trivial module. What's that? R is this ring here, sorry. So it's this finite étale extension that we passed to. And so we're looking here at Galois cohomology classes of the cyclotomic field Q zeta 13 with values in Z mod 19Z that are unramified outside 13. So that can only exist if you have a non-trivial homomorphism from this Galois group. So the kernel of it will be some field extension of the cyclotomic field Q zeta 13 of order Z mod 19Z. So cyclic. There's no such thing. There's only the cyclotomic extensions that give you these finite abelian extensions unramified outside of 13 here. And so 19 certainly does not divide them. So this guy is actually 0. Since there are no Z mod 19Z extensions of Q zeta 13 that are unramified outside 13. So a class field theoretic statement really is what is needed here to show that in fact this module is just completely trivial. Injectivity is a trivial statement. Okay. All right, so wrapping things up, we showed injectivity on both of these pieces. For one, we used the trick that we already had last time, just pass to the flat topology to use Kumar theory and get your estimate in this way. For the first, we use the kind of more arithmetic statement about the non-existence of unramified extensions with Galois group Z modulo 19Z over Q zeta 13. So very different kind of techniques coming together in this way to show that in fact the map 2 is indeed an injection. And since we know that 1 is surjective, so the co-kernel here is trivial going into here, and this map is injective from the co-kernel, and this map is injective, the co-kernel of this map must actually be trivial because it commutes. So the same argument as we did before, we just had to work a little bit harder to show the injectivity and surjectivity compared to the 5 descent that we did before. Okay. Okay. Any questions about this? It's a bit of a complicated diagram chase, but hopefully some of the key ideas came through nonetheless. If you want to let it sink in and look at the notes, the details, there are more details there. And of course, the original paper of Maser and Tate contains much more. Okay, so I'm going to erase all of this. and give you the conclusion of this kind of argument. Oops. So we conclude after all these diagram chases that in fact, if we take the abelian variety, the Jacobian of x113, and we quotient out by the image of pi, that is in fact trivial. That's what we showed. So how do we conclude from that the rank is actually 0? Well, there's several ways. One is kind of nice. Let's use the advantages that we have in front of us. In fact, this A of Q is also a module over the endomorphism ring. In particular, it's a module over the Eisenstein integers. The Eisenstein integers are a PID, a finitely generated module over a principal ideal domain. So it decomposes as a free part modulo something else. And since if we quotient now by a prime element, we get 0, the free part had to be 0. And that's how we conclude that it's torsion. And then we knew that already we found all of the torsion. So let's maybe write that down. Since AQ is not just a finitely generated Z module, but it's actually a finitely generated Z zeta 6 module. And Z zeta 6 is a principal ideal domain. So AQ is also isomorphic to, well, some torsion part times, I guess, Z zeta 6 to the power, let's call it, I don't know, let's call it S. To not confuse it with the rank over Q. Of course, they're the same thing. Okay. So we found after this 19 descent that in fact, it is true that the Mordell-Weil group is of ranks. So we've completed step 1 in our whole program to determine the rational points on the modular curve x1 of 13. The question is, how do we continue from here? Well, we have several options. The first, which is a very obvious one, since we're at a conference where Chabotis is a very important method, is use Chabotis. Question: how do we now continue to find the rational points on x113? They're no longer the same thing, the abelian variety and the curve whose Jacobian it is. So that's option 1. Use Chabotis. This is possible. Classical Chabotis that Samuel talked about. Since certainly, I mean, the rank is equal to 0, which is strictly less than the genus, which is equal to 2 in this case. We also have an explicit model. You can find it in the notes. I didn't write it down, so I'm not going to reproduce it here on the board. So look at the notes if you want to see what that explicit model over Q is. So some explicit equation that describes this hyperelliptic curve. So now all you have to do is pick your favorite E not equal to 13 and go nuts. And it's quite nice to try it. So since we're at this conference, this might be a nice example to try and see if you can implement the methods that you've learned about in this course. Of course, in my course, the whole reason for this course was to also look more at the number theoretic properties of the modular curves, rather than just viewing them as curves and equations and taking it from there. We're actually going to see if we can do it also maybe without Chabotis, and that's what Maser and Tate, or actually this argument was already known before Maser and Tate. I think it's due to Og. So there's an option 2, which I'll also discuss. because that is a step that later on becomes very important when we prove the general case. That's option 2. Option 2 is to do a moduli theoretic consideration. Is to say, suppose that there are some other rational points besides the ones that we found from the cusps. What do we do then? Well, we're going to consider the Abel-Jacobi map as we did before. So from x113 into its Jacobian by sending a point x to x minus the cusp infinity. So that's going to be my base point for this Abel-Jacobi injection. Okay, so I can do this certainly over Q. I can spread it out to Z1 over 13 also if I want. And now suppose, for the sake of contradiction, that actually there is a non-cuspidal rational point. Let's call it X. I know I called this X, but I can change this one. So it's non-cuspidal, so it's going to lie on Y1, 13, the affine part. And I'm assuming that it's a rational point. I want to show that such a beast does not exist, using just the fact that the rank of the Jacobian is equal to 0. Now, using the moduli interpretation, this will correspond to an enhanced elliptic curve, E comma P, where E is a rational elliptic curve, so it's defined over Q, and P is a rational point of order 13. Now you see, what we can do is we can reduce this point modulo a very small prime. When I say reduce the point, I don't mean this point, I mean this point. So on the modular curve. Try and keep the two separate in your head. So I'm going to take this point x, and I'm going to reduce it modulo a small prime. And that's kind of problematic because that tells me something about the elliptic curve, just the fact that it has a point of order 13. For instance, if I reduce it modulo 3, that elliptic curve can't have good reduction. Why is that? Well, because the number of points that you can have over F3, it's very small, right? It's 3 plus 1 plus twice the square root of 3. Certainly less than 13. But I know that the 13 torsion should inject modulo 13. So that can't really happen. It can't have good reduction. So by the Hasse bound, this curve E cannot have good reduction. In fact, if we elaborate a little bit on this argument, it can't even have potentially good reduction. Because if it had potentially good reduction, it would be additive over the base field. And the Néron model would be an extension of degree at most 4 of the additive group F3. Still no luck. You can't put 13 inside of there, so also potentially good is ruled out. Despite the fact that we know that the Néron component group here will be of size at most 4 by Tate's algorithm. Okay, so that means it's got potentially semi-stable reduction, right? So it must reduce to one of the cusps, modulo 3. Can't reduce to an affine point. Okay, so let me just complete this sentence because I didn't write it down on the board. Since 13 is not allowed to divide the number of F3 rational points on the Néron model of such a curve, it has potentially good reduction. Okay, so what we conclude from this is that the reduction modulo 3 is actually going to be a cusp. So there's 12 options. Yeah? There's 12 cusps that we have on this. Well, it can't be a non-rational cusp. That's not possible because the non-rational cusps, actually modulo 3, they're not defined over F3. They're defined over F27. because of that field extension that they are defined. So it's one of the rational cusps. It's one of our 6 rational cusps that we have in the reduction mod 3. And then, if I have this curve, I can use my super important diamond operators to translate it around, and I might as well assume that it's infinity, because that action acts transitively on the 6 rational cusps. So we may assume, we see that X reduces to a cusp modulo 3, and by the reasoning I just gave you, we may assume, without loss of generality, that that cusp is infinity. Now, that's a little bit funny, because if we look at the associated point in the Jacobian to X, then 2 things need to be true about this divisor that seem kind of contradictory to each other. Because you see, it follows that the divisor X minus infinity on the Jacobian, it must be 2 things at the same time. It must be contained in this Pro 3 group, which I guess we called it, we actually gave it a name before, called M, but I'll just call it with Silverman's notation now. So A superscript 1, yeah? So that's all the points reducing to the identity modulo 3. Yeah? That's a Pro 3 group. And in fact, I told you already, it's isomorphic to Z3 squared by the formal group law. So in particular, it's torsion free. And that's what we get from this statement, that it reduces to the cusp. So mod 3, you get the identity, and therefore, in the Q3 points, this point actually lies inside of the connected component that reduces, inside of the points that reduce to the identity. So that's a torsion-free group. On the other hand, it's a rational point, right? So it's also contained in A of Q, which is entirely torsion. These 2 things seem quite contradictory to each other. The only option is that, it's a trivial element. So X had to be equal to infinity. And that's a contradiction. Okay. It's a very simple argument. You don't really have to do too much work. You just consider the moduli interpretation, and you deduce from the fact that it has rank 0 immediately that you must have this property. Now, the luxury that we had here is that really we were working with the Jacobian of the full modular curve. And that's something we'll come back to later on. So in general, you'll see if you keep extending these arguments, and I encourage you to do that, you'll run into more and more trouble. So for instance, here we've fully finished the argument for 13, so it's very logical now to go to 17. And the literal analog of what we've done here would be, well, to look at this Jacobian of J117 to show that there's no points on X1 of 17. The first step would be to find the rank of that Jacobian. Now, the rank happens to be 0 in this case. So, okay, so maybe the strategy there is not quite in trouble yet, but it's a much bigger thing, right? So I wrote here, it's the genus of this curve is 1 plus 4, which is 5. But I mean by that the Jacobian splits up to Q isogeny as an elliptic curve and an abelian fourfold. The elliptic curve is a familiar one. It's actually the Jacobian of X0 of 17. X0 of 17 is an elliptic curve, but there's also this new bit, this fourfold that's inside of it. So if we were to do the same kind of argument on X1 of 17, we'd have to show that both of these pieces are rank 0. No problem, you say. Okay, we're going to do our flat descent. On X0 of 17, I'm going to do my 4 descent. Already a little bit trickier than what we did, because the spreading out the special fiber at 2 is riddled with technicalities, so you have to be very, very careful in your application of OR-Tate there, for example, which the ramification is now big enough for that to potentially fail. So you have to argue more for that 4 descent. For that 73 descent on that 4-fold piece, the argument is very similar. So it's a very instructive thing to try and generalize it here and to show that the rank is indeed still equal to 0. and to then conclude in the same way that we just did with essentially the exact same argument. In fact, the argument becomes even stronger because now it's 17. Reduce mod 3, the Hasse bound is even more violated. Okay, so using these kinds of techniques, you could bring this to a good end. But then you realize, well, actually, that was maybe a little bit silly. Maybe we didn't have to deal with this fourfold part. Maybe we could have skipped the 73 descent and just dealt with the x naught of 17. Because after all, if we have a rational point on x1 of 17, we can map it down to x0 of 17 and do the argument that I gave here on the lower curve. And it still works. And that would be a first step where you could save yourself some trouble. So that would be what you do here. So you already learned that actually the two together seem to play a very big role, just like in 11. Yeah? So the isogeny between them was very important, and we use information from both curves. Here also you learn that at 17, this kind of thing also happens. 19, the very similar structure to what we saw before. The dimensions get bigger, but in this kind of argument, that doesn't really matter all that much. Here, 23 already, it's a little bit different because now we don't have an elliptic curve anymore. We have an abelian surface here for the Jacobian. So that's already a little bit bigger. But then the biggest obstacle comes at 37. Suddenly at 37, you're going to have to do a whole new thing. And that's the last thing I want to tell you about. And if you play around with these kinds of structures, you actually come pretty close to something that approximates Mazur's argument fairly well. So in general, it is not true that J1 of P has rank 0. And that's really very important for this kind of argument. This argument that I sketched here, the fact that it was rank 0 was very important there. In fact, even worse, it's not even true that J naught of P of Q has ranked 0. So that's a problem, right? These Jacobians don't have rank 0 anymore. Already for 37, you have two elliptic curves, one of which has rank 1. So you can't work with the full Jacobian, is the conclusion that you come up with. You see that in 37, if you do that example, the Jacobian has rank 1, but it still has this elliptic curve inside of it, up to isogeny, which is rank 0. So maybe you can use that and an argument along these lines to conclude in exactly the same way after you've done the descent in the same way. And that's exactly what Mazur did. So he looked at this argument, and he actually wrote down the bare minimum of what he needed to run this argument successfully. This is called a formal immersion criterion. So the first thing that Mazur does is he shows that there is always an abelian quotient, meaning of the abelian variety. I don't know why I called it that. From J0 of P onto A. So there's a piece, there's a quotient of A that does have these properties. So two properties need to be true. Well, for this kind of argument to run, it better have rank 0. Yeah? Maybe the full Jacobian didn't have rank 0, but maybe there's a piece of it that still does. So that's certainly a property that we want on this list. Yeah? So AQ needs to be finite. Okay. The second part is that you see, we've lost a lot of information. The curve sits inside of this Jacobian. It doesn't really sit inside of this abelian variety A in general. So we want somehow that this quotient is big enough that it remembers enough about the original curve to run this kind of argument. And if you unpack the argument, you see that the minimum you need, or what would be enough, and in fact, you can get by with even less than this, but that doesn't really matter. If I take the curve x naught of P, and I extend it to Z1 over P, let's say I stay away from the bad fiber, to the neural model of this quotient over Z1 over P. I want at infinity to be able to run this argument. So I want to be able to conclude something in the set of QP points that reduce to the identity mod P, which is this free group, so it's torsion free, and then we can still run the same kind of argument as long as that map on the formal neighborhood, which is all I need for this A1Q3, is surjective. So this map must be what's called a formal immersion. At infinity. So that means that if I take the completed local ring of my neural model at the identity, like so, I certainly get a map to the similar object for x along J. Yeah, that's the pullback map along J. So x naught of P around infinity is surjecting. In fact, and that's a good exercise to do actually, if you look at this argument, try and show that whenever you have such a quotient that satisfies 1 and 2, actually you successfully showed that there's no non-cuspidal points on x1 of P when P is larger. It's essentially the same argument. You just have to make a few adjustments. It's a very instructive exercise to do. And that'll also make you appreciate why this condition is so important. Now, one thing before I finish that I would like to mention is that, you see, now it's reduced to some axiomatic statement. All we need is a quotient that satisfies these two things. Now, how you find such a quotient is up to you. Ideally, you'd like to think that maybe A has to be somewhat big for the second one to be true, but it also has to be somewhat small for the first one to be true. So there's a balance to be struck between the two. Now, what Mazur does in his original paper Mazur constructs such a quotient well, he constructs such an A, and he calls it, I guess is the right way to say it, he calls it the Eisenstein quotient. It's a quotient that comes from a certain ideal in the Hecke algebra that essentially measures all the Eisenstein congruences. So TP minus P plus 1 are operators that span this ideal. Now, where does that come from? In fact, if we look at this table, we already get a little bit of a hint. This Eisenstein quotient, whatever it is, however it's defined, you want to show that it's finite, yeah, the model Weil group. So you want to show it has rank 0, and for that, you're going to want to do some descent with respect to some prime. And so we profitably used the primes that appeared in this little table here. And what Mazur's going to do is, well, he realized already he can work in the top layer. So he's dealing here with torsion that has a very predictable order. It's the numerator of P minus 1 over 12, yeah, which always has some non-trivial primes inside of there, and they're always co-prime to P. So you can run an argument along the lines of what we did today. And what does that have to do with Eisenstein series? You see, P minus 1 over 12 is the constant coefficient of an Eisenstein series. There's an E2, there's an Eisenstein series of weight 2 on gamma 0 of P, which is the P stabilization of the one of level 1 that doesn't really exist. It isn't really modular, but after P stabilization, it is. And this is essentially its constant term. So if we have a prime that divides that numerator, then modulo that prime, the constant term vanishes, and this Eisenstein series looks like a cusp form. Yeah? So that's where we kind of get our first hint that these primes, these descents that he's going to be doing, have something to do with congruences between Eisenstein series and cusp forms. They're very closely related to each other. In fact, the same is true for these primes that we saw here. But yesterday there was a question, what are these primes? Well, I still can't tell you, they are what they are. It's a bit hard to say, but at least we have another, arguably more mysterious interpretation. They are also primes for which there are congruences between Eisenstein series and cusp forms for similar reasons. So these B2 chi's are also the constant terms of Eisenstein series on level gamma 1 of P this time. So the product here, prime dividing that, there will be a prime in some extension, cyclotomic extension, for which there is a congruence between a cusp form and an Eisenstein series. So the construction of this quotient, it achieves both of these things. That's what Mazur shows in his paper. But it's actually super interesting just in its own right. Yeah? It far surpasses in importance just the application to this particular problem of classifying the full torsion. Nonetheless, that is what Mazur does. He constructs such an A. He runs arguments very similar to what we just did. And I guess I can't end without at least stating this theorem. This is the theorem that he proved in this 1977 paper. Actually, I didn't write it down, so hopefully people will help me if I make a mistake in the statement. But let E over Q be an elliptic curve. Then if I look at its torsion subgroup, it's isomorphic to Z mod NZ, where N is 1 all the way up to 10, 11, not possible, we already proved that. The 12 is possible, 13, no longer possible, we also proved that. But he proves this fully general theorem. So that's this spectacular landmark theorem, which he proved very much using the techniques that we used after he constructs the Eisenstein quotient and shows that it satisfies these two. Now, like I said, the importance of the Eisenstein quotient surpasses the application here. And in fact, next time we'll see that just for this application, there's other very convenient quotients that we might take. So there's been more recent advances since the work of Maser due to Gross-Zagier and Kolyvagin, which I'll discuss next time, that allow you to construct such a quotient much more easily, in fact. So that allow you to construct such a quotient, deducing the finiteness, it's called the winding quotient, we'll talk about that, by analytic means. Because these methods will prove enough about the Burton-Swinnerton-Dyer conjecture to be able to conclude by analytic means that the quotient, the winding quotient we construct, will be finite. So no more descent, except, of course, there is some descent somewhere. The descent is in Kolyvagin's work then, which is arguably, an even trickier descent. But if you're willing to take that as a black box, that allows you to construct this quotient with much more ease. And then all you have to do is show that it satisfies the formal immersion criterion, which is still work. But that is, in fact, a key technical innovation in the generalization due to Mirel of this work of Maser to higher number fields. So more on that next time. See you then.
Any questions?
Sorry?
Could you explain about the formal immersion? What is the rule?
It's this. This is the definition.
Yes. Geometrically, how to see this? You said x naught of p will be inside j naught of p, and that doesn't inject into A, and then you want to retain some information, etc. Just could you elaborate?
Exactly. So if you're just embedding into the Jacobian, this is automatic. This is actually an immersion. It's actually an immersion of schemes. Yeah? But if you just map to a quotient now, you lose some information. There's a kernel to this, which could be quite large. So you're in a much lower dimensional variety. And so you want to know that at least in this formal neighborhood, which is what we need to run this argument, the pullback map on functions on this quotient still sees all of the functions, at least in the formal neighborhood around infinity on the curve. And that's all you really need. So this is the definition of a formal immersion. In fact, so you have such a map, right? It's the Abel-Jacobi map, composed with the quotient. So the map J is defined, the map J upper star is defined, and I'm demanding that this is a surjection. That's a definition of the formal immersion. Well, that's the exercise in a way. Yeah. So why that's enough to run this argument? Yeah, that's exactly it. In fact, you don't need to tweak that much. It's very similar. So you just, instead of looking at x, you're going to look at the image of x on x naught of p, reduce that modulo 3, let's say. 3, so 3 had better be a prime, I guess, that is allowed here. Yeah, so here I've done it over z1 over p. Yeah, so that's okay. That's very strong, but maybe 3 is already close to what you need. You reduce it modulo 3, and you do the same thing. So you just reduce it in the Jacobian of A. I've even called it A, so you don't have to change that much in the proof. And you see that that's really all you need in the argument. So the argument is virtually unchanged after mapping it down to x naught of p. So with that same argument, you show that this is all you need. These are the axioms. Yes. Can this be extended to Mann and Mumford? Yeah, I'm not sure what that means. I see, I understand. That's a good question. Actually, I'm not sure. But for this, you will want to look, I think, at Matthew Baker's paper. So Matthew Baker runs an argument that uses very similar ideas, actually, to conclude something along those lines. So I think the answer is contained in Matthew Baker's paper, if I understood your question. Yeah.
Any other questions?
Ah, yes. Yeah, Barry Mazer really likes this statement, this accidental, yeah. No, so in fact, 37, yeah, that's an excellent comment. So 37 doesn't really play a special role in the argument of Mazer, as far as I know. It's just that if you approach it in this very naive way, where you do it step by step, right? So one option you could have is you want to learn about the work of Mazer, you take Mazer's paper and you go to section 1 and you read, but that's kind of a wall of technical stuff. So what we could do is we can try and approximate it step by step and run up. And it's only if you do that at 37, you'll encounter this difficulty where you can't work with the full Jacobian J naught of P anymore. You have to pass to one of these quotients. So the Eisenstein quotient or the winding quotient are the same in this case. They're actually a non-trivial quotient in this case. But in the actual argument of Mazer, 37 doesn't play any special role. So he does it fully generally. So he certainly doesn't need to exploit this additional piece of structure that lies there, even though it is interesting in its own right.
Is it true that the roadblock at 37 comes because it's an irregular prime? Like it's the first irregular prime that you hit?
Yeah, indeed. So I didn't actually mention all of this, but there's lots of connections with class numbers of cyclotomic fields, which you have to get into if you actually read Mazer's paper. Here you already get maybe a little bit of a clue. This looks like, I mean, yeah. So this thing, it's the order of K2 of the ring of integers in the totally real cyclotomic field, conjecturally, if we assume Tate Lichtenbaum. The K0 would be the class group. You get very similar expressions. So class groups, class numbers of class groups and divisibility of them, very closely related to this kind of area. So certainly 37 is special from that point of view, in that the class group is actually divisible by 37 in that particular case. And those kinds of arithmetic statements come into the argument, certainly in a big way. And that's also what makes the Eisenstein quotient so rich and interesting to look at. Yeah, absolutely. 37, by the way, also has a rational point. That's non-cuspal.
Any other questions? Yeah.
Ah, yeah. Right, thanks. Yeah, I should have pointed that out. Indeed, yes. Absolutely. Yeah. Yeah, indeed. Thanks.
Any questions, remarks? I guess not. So let's thank speaker again.